This is the final synthesis project presentation for mitotane, which is this molecule right here. So first, of course, we start with benzene. Then we can chlorinate it with Cl2 and FeCl3 through an electrophilic aromatic substitution. And then we can do a Friedel-Crafts alkylation with chloromethane and aluminum chloride. That will add to the ortho position because chlorine is a ortho para director. It could also go into the para direction, but since chlorine is it's just one atom, so it's not very bulky, and neither is chloromethane, so you'll get a lot of this ortho product. After the Friedel-Crafts alkylation, we can add chromic acid and heat to turn that carbon bonded to the benzene into a carboxyl group. This is possible because on that carbon bonded to the benzene, there's hydrogens, and that results in this product with chromic acid. Once we have that acid group, we can react it with SOCl2 and heat. That will just replace the OH group that was there with a chlorine, and we'll get this acyl chloride. Once we have this, we can do another Friedel-Crafts acylation, and we will use this chlorobenzene that was made earlier, and we will add this to the chlorobenzene. So we need aluminum chloride for that, and it will mostly add to the para position, since again chlorine is a ortho para director, and this group is very bulky, so it'll be away from the chlorine mostly. Once we have this, we can do a Wittig reaction with a phosphonium ylide, and the synthesis for this phosphonium ylide is below here, which I'll go through quickly and then I'll come back to this. So you start with triphenylphosphine, and that does an SN2 reaction with chloromethane. So this phosphorus will push off the chlorine on the methyl group, and it will bond to that methyl group. And after that, you can add a strong base like butyl lithium, and that will take a hydrogen off this carbon, and the electrons that were in that bond between the carbon and hydrogen will instead be a pi bond between the phosphorus and carbon. So once we have this ylide, again we can come back here and react that with this molecule. And what that should do is it will replace this oxygen in the carbonyl with whatever's bonded to the phosphorus. So that's a CH2 group. And there is one concern about sterics, because this is a fairly sterically hindered carbonyl since it's flanked by two benzene rings. So there's a possibility that sterics might be an issue here. But if we get this molecule, we have a double bond that can then be added to with chlorine. So this is an addition reaction where chlorine adds, you add a chlorine to each carbon in the double bond. And once we have that, we want to eliminate one of these chlorines, and we can use a strong base like ethoxide. And preferably, this should be done in heat probably, just to avoid any SN2 reactions with this top chlorine. But the E2 reaction is heavily favored because if you get a double bond here, it's conjugated with two benzene rings. So the E2 product will probably be the major one. And there's only one elimination product possible since there's only one hydrogen that's extractable, which is at the top here. So taking off that hydrogen will make the electrons in the bond to that hydrogen fold over, kick off that chlorine, and you'll get a double bond here. Once we have this molecule, we'll do another series of similar reactions where we do an addition reaction with chlorine, so adding two chlorines again to the double bond, and then another E2 reaction with ethoxide to remove that bottom chlorine. And finally, the last step is to remove this double bond. So we can do that by adding hydrogen gas and palladium on carbon. This is a reduction reaction. It'll add 2 hydrogens to that double bond, and you'll get the saturated carbon bond. So that's it.